Thank you kindly. I promise I'll be succinct, 5 minutes. Background, I'm a full-time clinician and cataract surgeon, and really I feel like I'm a novice in a room of experts. So in that context, I'm going to share with you what I did, what worked, and what didn't. For me, the critical first step, which was kind of a one-way door and a point of no return, is how the data would be pre-processed to fit into a model. So what I did is I took the OCT images and basically generated broad slices that were aligned with, or the fundus photos, I should say, and generated broad slices that were aligned with the OCT images. I wanted to basically align them and focus on the relevant areas, but I didn't get super detailed with that. I tried some other things. I tried an AI-generated mask. That didn't work. I also tried to include in the training data just a plain normal OCT image for everyone to see if that would help get my model kind of a jump start. That didn't work either. Okay. Then I got to that one-way door, where the one-way door is, once I committed to what the training set would look like, it would be very rigorous to go back and redo that. So on I went. In terms of different models, it's fascinating to me, and I congratulate the winners, that they used a diffusion-based model. That didn't work in my hands. 95% of my efforts were using the pix-to-pix model. And that there's basically freely available an implementation of that on the internet, which I heavily modified. So I'm not going to summarize the pix-to-pix model, but I'll say what I did was kind of a novice low-budget method using cloud computing. I used DigitalOcean paper space gradient to get access to single NVIDIA, usually A6000. Basically, you can get what's available at the time. I used DigitalOcean spaces, Microsoft OneDrive storage, and my costs were $60 a month. With this, basically, I could train the model such that each epoch took about 5 minutes. I could get to 100 epochs over the course of a single business day. This is kind of a brief video of the interface that you can see, where you can see what kind of the parameters look like, and more importantly, what you can see is the number of parameters in the generator portion of this model is 200-something million parameters. The number of parameters for the discriminator portion of the model is about 11 million, and you can see that here. So in that context, if you think of all those parameters, my trying to do that initial feature selection was very naive, I think, and it's not a shock that that wasn't terribly useful. This is one training run. You can see kind of a representative sample of the output images, and you can see how the model is starting to learn kind of very low-level detail in the beginning, and already by kind of epoch 15, you can kind of start to see something that looks like what we would recognize as a scaffolding of an OCT image. I locally kind of created custom scoring, so I could create a proxy for the FVD and FID score to try to hone my models before submitting them. This was constrained by the fact to do that scoring, that actually also requires a lot of compute power. So what worked and what didn't work? To use the pix-to-pix model, you can't use rectangular images unless you crop them to squares, so I cropped them to squares. Learning rate was important, and I kind of usually started with a little higher learning rate and then honed it down at the end. My highest scoring model ended up being one that had 195 epochs. I experimented a lot with the lambda, and all this is kind of publicly available in terms of what these parameters do, and it turns out that the default ended up being the best performing for this task. Initially, I was only saving every 10th model and looking at every 10th model that I created. And it turns out that was very naive, because when you look at how these are generated and the injection of randomness with every epoch, that was a silly thing to do, and I really needed to look at each and every one, and that's what I ultimately did. I didn't change the kind of default generators, but I did try something where I created a custom loss function emulating or trying to emulate the FVD scoring, and that was very compute intensive, but ultimately did not add value when it was all said and done, but seemed to be a promising thing to do. So the end of the road. These are 3 randomly selected images from the test set that were generated on Friday, And that kind of gives you an idea what the final output of this looks like from a human perspective. So I'm not going to go into great detail here, but basically I brought my 32 best models to the competition on Friday, ran them all using kind of this brute force method, and it turns out the whole thing worked pretty well, surprisingly. I learned a ton in the process, and I think we should take time to really commend the organizers of this activity, because this is really a high-quality data set and event. It's a very appreciative and impressive thing, and it really catalyzed a lot of activity and a lot of learning for all of us, so that's pretty impressive. I think the rest of the conclusions maybe will appear in the final summary, but I think to make this more meaningful, we have to come up with kind of loss functions and evaluations that focus more on the clinically relevant, important parts of kind of the finally generated images, and that's probably not a unique observation. So thank you again. I really appreciate everything. This is really a wonderful activity.
So I think I would like to thank Michael for you're very brave. You spent all this, you cover all the costs, travel all the way to Hong Kong and complete the finals. Thank you so much. Congratulations.